Hello, welcome to the RMG workshop section on Arcane. So, the point of Arcane is to take quantum chemistry calculations and use statistical mechanics and different corrections to give you thermochemical and kinetic parameters. There are a few other softwares for doing this. The most famous are MESS and Mesmer. Arcane's sort of differentiation is that our software tends to be a bit easier to use, um, and a bit more focus on user friendliness. Um, so broadly, quantum chemistry calculations give you an energy value of the lowest energy geometry and the 0 point energy at that optimized geometry. You can also use it to locate saddle points for looking at transition state calculations. And you can also calculate the Hessian with respect to the molecular energies at particular geometries, which is related to the frequencies. And you can also use it to calculate rotor scans, which we'll talk about a little bit later. But broadly, when we think about running quantum chemistry, usually we're thinking about obtaining optimized geometries for both conformers and for saddle point transition states, and also for getting molecular frequencies. It's hard to talk about all of this without talking about partition functions. So the partition function Q describes the distribution of energy levels within a thermodynamic system. And the quantum mechanical one for a molecule differs very significantly from the classical. In particular, we're able to use these partition functions to calculate thermodynamic properties here, which enable us to calculate thermochemistry from this partition function. So typically you would decompose the molecular partition function into a couple different components. The translational component here, related to motion of moving the molecule in space without changing anything relative to each other. External rotation, which is rotating the molecule where all of the atoms are the same distances apart. And then there's the vibrational component, which is essentially kind of tends to be moving sort of the primary other motions, which are sort of motions that tend to change bond lengths and may be related to some internal rotations. And then there's also an electronic component. Once we have the partition function, it's quite easy. It's these sort of basic StatMech formulas enable us to get entropy, enthalpy, and the heat capacities, which gets us our thermodynamic properties. So that gets us our properties, but sort of embedded in what we've talked about so far is the rigid rotor harmonic oscillator set of assumptions. That when molecules rotate externally, the atoms don't move, and that these internal motions obey harmonic oscillator potentials. And these are very useful approximations. And oftentimes, when people typically talk about improving beyond this, they often talk about corrections beyond RRHO. And so this is kind of it's a good base point to sort of think about things. However, it's not a terribly great assumption because although it works very well. In fact, it works a bit better than you would expect. But in many cases, molecules aren't stuck around their lowest energy geometry. In particular, and they may have degenerate lower energy geometries. If you do internal rotations, you may obtain other geometries with the same energy. Or you might just have other geometries you could configure it in that have similar energies and that may also be populated that are far away from your initial geometry that you've assumed that everything is a harmonic oscillator about. One very common case of this is hindered rotors. And in many cases, the molecular geometry can be easily changed by internal rotations about bonds. For example, in this CC bond over to the right, this can be each of these can be rotated around this bond. And these rotations tend to correspond to low frequency motions and typically have very low barriers. And because of this, the states of these rotated molecules contribute significantly to the partition function. And these can have a very strong impact on the entropy of the molecule. The most common way to handle this is you project out the low frequency motion that's associated with this rotation and replace it with a partition function for a 1D hindered rotor, which requires running a rotor scan essentially to get the energy profile as you rotate about this bond. If two or more internal rotors are tightly coupled, which can happen when you have longer, more complicated molecules, especially with hydrogen bonding, it can be necessary to use more expensive high-dimensional treatments. Arcane supports use of ND semi-classical and can call Q2D-TOR to compute 2D quantum mechanical rotors for these situations. So a bit more broadly on calculating accurate thermochemistry. Running high accuracy quantum calculations is very expensive, so it's important to try and get as much accuracy out of each calculation you run. You should always be using atom corrections to calculate the energies relative to the energies of that element, the elements at that level of theory. That's very, very standard and should always be done. Although you can you can also additionally help that sort of to improve things, and what's typically done to sort of account for more bond aspects is sort of estimating a shift between the level of theory and experimental, and then sort of applying that correction across a space of a PES of different potential energy surface of different related molecules. You can also use bond additivity corrections, which is Arcane's preferred way, which is essentially there's a set of energy corrections associated with each bond type relative to experimental data that it'll add that correction to, which greatly improves the accuracy of Arcane's thermochemistry calculations. Arcane also now has an isodesmic reaction scheme, which uses a database of experimental thermochemistry to automatically construct a reaction that preserves the atom and bond type, that includes the target species and a set of molecules with experimental thermochemistry, and that allows you to get a very similar sort of to be able to correct it very similarly to bond additivity. So far we've mostly talked about thermochemistry, but for rates, for most cases where you do have a barrier, you're talking about transition state theory. And if you aren't, if you have barrierless reactions, you often talk about variational transition state theory and some more complicated methods. But we'll talk primarily about transition state theory. And it provides us a way to compute rate coefficients statistically mechanically. And it essentially relies on this equation here and this ratio between the partition function of the transition state and the partition function of the reaction, and the energy difference between the TS and the reactants. So unlike thermochemistry, we actually get some very nice natural cancellation of errors for reactions when we divide partition functions. And this makes it a lot less necessary to have bond additivity corrections. And we don't have bond additivity corrections for transition states. That's something that's still being studied. But it's usually more accurate to compute them without using the corrections, because if your calculations are at the same level of theory, there's a lot of really nice cancellation that's very helpful in getting accurate values. Tunneling corrections can be very important when light atoms are involved with the transition state, and would be another additional factor in this equation. So now we'll go through some Arcane examples and practice running Arcane and sort of talk about what the input files look like, etc. So for this, we're going to go take a look inside the examples folder in RMGPy. Note I'm in the RMG environment and in the RMGPy directory. Going into examples, Arcane. We have a set of folders here. So first, we're going to sort of talk about thermochemistry calculations for species. So let's take a look at ethane. So we've got a number of files here. These log files are calculations, are quantum chemistry calculations. This is the rotor scan file, and this is the energy file, and I believe this is the frequencies file. This is the input file, the main input file, and this is an input file that's a sub-input file that's specific to ethane, which can be handy to have. So in this case, the input file is quite simple, actually. Tell it what model chemistry. This use hindered rotors is a nice little trigger that lets you turn it on and off. This tells it to not use bond corrections here. And then this tells it what the species name, the file to get it from, and the structure of the species, and then requests NASA polynomial thermochemistry for C2H6. And we can look at the C2H6.py, which has all the sort of information related to ethane. It tells it how many bonds of each type of bond. It tells it whether it's linear or not. Although a lot of these things Arcane can guess itself now. This pulls the geometry and frequencies from the CBSQB3 calculation log file. And then here, as you can see here, it has one hindered rotor that it associates with that scan log file. These pivots are related to the ordering in the log file because it matters. It needs to know what bonds it's rotating. And the pivots are the two bonds that it's rotating, and then this defines one side of the molecule that's rotating relative to the other side. And this tells it whether to use a Fourier or cosine fit. In this case, it will do both, and it will take the best one. And we can run this. My command for this is arcane run. But you may, in your case, you may want to do back directory to arcane.py. And you can see here it loaded the database, determined statistical mechanical parameters, picked the symmetry number that we saw that wasn't inputted into the file, but is the case. Identified the point group, and then saved thermo for it. And now you'll see we have a bunch of other files, and we can look at the output file in particular. This tells us what the coordinates were, the general sort of statistical mechanical properties that it pulled out of the log files, and the thermodynamics for C2H6. We can take a quick look at benzyl, which is largely similar. You've got a frequency file, an energy file, and a rotational file. In this case, it's even simpler. It says use bond corrections, use hindered rotors, what the model chemistry is, the species, and it asks for StatMech calculations and thermo. Benzyl, sort of giving it the bonds associated with benzyl, these properties, telling it to get it the energy value from the energy log, and then taking the geometry and frequencies from the frequency log, and the hindered rotor from this log. And we can once again look at the output file gives us our coordinates, our information here, and the thermodynamic parameters. We can also, there's also a number of other files that you've probably noticed here. Hindered rotor scan data has the information related to the hindered rotor. Supporting information has some information related to the quantum chemistry. Information pulled out of the quantum chemistry. The arcane log file just has the information printed out during the run. And chem INP is the chemkin file that has the Ness polynomial in chemkin format. Plots has a number of other sort of plots for the rotor scan, and I believe thermochemistry information. But let's upgrade a little bit and go in and take a look at a reaction, what this looks like for a reaction file. So let's look at methanol plus HCO. And so if we look at the input file, we're doing a little bit different model chemistry here. Can set the frequency scale factor here, otherwise it will try to pick it automatically. We give it the species. We also define a transition state because it's a reaction, and so we need the statistical mechanics around the transition state, and then the other species, and then we define the reaction as it happens. In this case, it's just an interchange. We can look at let's look at the TS, which essentially tells it where to get the energy and where to get the geometry and frequencies around the transition state. And this doesn't account for hindered rotors, so there's no rotors in this category. And because it's a transition state, there's no real need to define the bonds for it, since we're calculating the rate, not the thermochemistry. And these ones look similarly. And our output file, and we get our statistical mechanics parameters, and then we get our transition state results. So this is the transition state, and this is with tunneling. And then this is the equilibrium constant in the reverse. And then at the end here we get our Arrheniuses with and without tunneling, and the Arrhenius parameters and the fitting information. So let's take a look at a pressure-dependent network. So with a pressure-dependent network, now we've got potentially multiple reactions, potentially multiple species. What you can see here is that this file does things a little bit differently, and most of these other ones we've been pulling from quantum chemistry log files, and this one, all of the parameters have been explicitly given for each of these species. We've got lots of species, lots of transition states, lots of reactions here. And then we have sort of our first new block, which is the network block. That essentially it labels lists all the isomers, which are wells that are not output or reactant channels, that are not product or reactant channels. And then also the reactant channel and the bath gas that's used for these calculations. And then we have the pressure dependence block, which tells us what temperature and pressure range to sample at. These parameters affect the master equation solution. RMG has three different ways, three different algorithms for solving the master equation: modified strong collision, reservoir state, and chemically significant eigenvalues. In general, chemically significant eigenvalues is the most accurate, whereas modified strong collision is by far the most robust. I think we'll in another session we'll talk a little bit about the differences between these methods. The interpolation model is what format you're going to get the output pressure-dependent rate coefficients in. In this case, it's requesting Chebyshev coefficients, which we generally recommend when you're using them with softwares that are compatible with Chebyshev. And then also a sensitivity condition, because Arcane has sensitivity analysis for wells, which essentially does a brute force sensitivity analysis. It perturbs each well and each TS energy level and looks at how that impacts, and then reruns the pressure dependence calculation, and then examines how that affects different rates in the pressure dependent network. So we'll run this right now. So we've got a lot more stuff loading here, and here it lays out what's in the network and the energy levels associated with each of these, and all the path reactions involved, the product channels, the reactant channels, and then the isomer channels. It did the main calculation, and now it's running the sensitivity analysis. So essentially it's perturbing the well by 0.1 kcal per mole, and then running the simulation and seeing how it affects the rate coefficients. And it'll do this for each well and each transition state, which will take a little while. And we have our results. So now we can look at our output file. And this gives us our thermo used, and it gives us our PDEP reactions for each. So this gives us our Chebyshev coefficients and for the associated pressure-dependent reaction. And then also this matrix relating for sort of if you're looking at particular values to do comparisons. And it gives you that for all of the reactions and all of the possible pressure-dependent reactions within the network. If we go into the sensitivity analysis, there's a lot of plots related to each reaction and each well. The text file here, which gives you these sensitivity coefficients for each TS and each well or isomer. And it does that for all of these reactions, but just at the temperature and pressures requested in the input file. And these can be used to tell what stuff's the most important in the network and what stuff you might want to improve or run higher level calculations with. It's also available on a YAML format here. When we run these, we also get PDFs of the network. I'll show you one of these at the end, but which are quite nice to look at and tell what's going on and useful for presenting work on these sorts of things. There's also a variety of plots here, but these are mostly sort of plotting the rate coefficients, the rate coefficient values for all of the pressure-dependent reactions. So we've shown you how to calculate these networks, but if you notice here, this is a lot of information, and it's a lot of painful quantum calculations to run. And especially, and this is even a relatively small network if you think of it. You can have much, much more complicated networks. And if you're running RMG with pressure dependence, you're going to see vastly more complicated networks than this, unless you're using very small species. And in a lot of these cases, it's really painful to have to calculate everything for all of those. And you'd like to be able to perhaps do what RMG does essentially, and generate a lot of these things and estimate what all of these are for you. And this is what we have the Explorer tool for. And let's go to the methoxy example. So in this example, we do include, we give it a database block. And this lets it pull information from RMG, run thermo estimates, run kinetics estimates, and integrate those into the network. And so essentially it will go through an iteration. It's not exactly like RMG, but it's similar to RMG, where it will automatically iterate through generating a network for you. But you can also, so we give it this database block to tell it where to pull information from, but we can also feed it in quantum chemistry calculations that we've run, and it'll integrate that into the run. So this is this taking the methoxy example, where we have some calculations that we're integrating into this, and some reactions. And then we define a pressure dependence block. And this pressure dependence block serves much the same purpose as the other pressure dependence. It sets all the parameters, what temperatures we're interested in, what pressures we're interested in, what method we're using. And then we define an explorer block, which essentially we give it a source, and essentially it tries to expand out, takes that source and looks at what reactions will be produced by that source, and what percentage of the flux is it will be traveling down each of these pathways according to the Explorer tolerance. You can also define energy and flux tolerances, which essentially cut off reactions that are too high of energy from the network, which can be helpful in solving these networks and also in sort of analyzing them, looking at them. You also define the bath gas, and also it can be quite handy to set the maximum number of radical electrons to avoid CH2 species, which can sometimes be quite useful. But here we're going to set it to 2, so those are possible. And so we're just going to run that input file. It loads up all the databases. And as you can see here, we've loaded up everything like we normally do. But now we have sort of a model enlargement framework here. And what we'll see is that it'll generate, initially it'll generate a few different pressure-dependent networks, but it'll focus on the ones that actually matter here. And it will take that network that we requested, the methoxy network, and it will start running it iteratively and adding stuff. And as you'll see, it'll start to get more complicated. And after a few iterations, it will finish. And we'll get an output file, which will give us, first will give us all the information related to those quantum chemistry calculations quantum chemistry information that we gave it, the frequencies and then it will give us our PDEF reactions. In this case, we requested PDEF Arrhenius, and so it will give us it in PDEF Arrhenius format. But here's the T&P. It'll also tell you where your thermochemistry came from and where your path reactions came from. And of course, here you'll have a much larger Chemkin file, although it's worth noting that this will include the base reactions and the pressure-dependent reactions, which you're probably going to want to separate from each other. It also all of these, I haven't noted it before, but all of these produce RNG libraries. For all the involved reactions. We can also look at methyl plus formaldehyde, which is a simpler one that doesn't have any quantum chemistry sort of fed in, and we just request it. And this one is actually going to is a bit interesting because when you do this, you can actually end up with multiple networks because the starting reactants may have multiple ways that they can react. And as you'll see when we run this, you'll get a network 0 and a network 1. And this Explorer tool can be quite nice, especially if you combine it with sensitivity, where you can run sensitivity analysis, determine what's important, add those parameters into the input file, and then rerun it until you have all the sensitive parameters accurately, and can be a good tool for making sure that you're not missing stuff when you're trying to deal with pressure-dependent networks. And now we'll take a look at these files. And here you can see the network drawing. You can see that sort of this one path where you add add to the O here, and you have this sort of path, but there's also this channel up here. Of course, oftentimes you wouldn't care about this sort of channel, and you could get rid of this by decreasing the number of radical electrons to avoid the CH2 group, or by setting an energy tolerance that would set an energy tolerance above the starting well that you care about. Now, the more complicated network comes when it adds to the carbon, and we get this pressure-dependent network here. And you can see the barrier heights, the well heights, and sort of what this sort of network might do depending on the temperature. These diagrams are quite useful for diagnosing what's sort of going on in these networks. So this is all I have to show you guys for Arcane. So hopefully this is useful to you. Thanks for listening.